Now that we have a basic theory of polynomials, we move on to rational expressions. A rational expression is going to be a polynomial over another polynomial. For instance, I could use 2 over x cubed plus x plus 1 over x squared plus 1. Two variables, we have st plus 1 over s plus t. We note, if we think of polynomials as having similar behavior to the integers, then rational expressions will behave like rational numbers. And then we'll have all the same issues. Now, for a blueprint, for polynomials, we have the 4 major operations: addition, subtraction, multiplication, division. Then we solve polynomial equations. Similar here. For rational expressions, we'll first do multiplication, division, then addition and subtraction, then we have solving rational equations. We have one issue first to deal with before we get to the major operations. So with rational numbers, we're always interested in putting our fractions in reduced form. Same goes here. If I want to simplify a rational expression, checklist. First, we completely factor the numerator and denominator. Then I cancel all like terms. Then note exponent rules apply. So for instance, if we had just a regular old fraction, 14 over 42, completely factor, so it'd be 2 times 7 over 2 times 3 times 7. The 2's cancel, the 7's cancel. We're left with a 1 on top, so I get a 1/3. For a rational expression, let's try 8x cubed plus 16x squared plus 8x over x squared plus 4x plus 3. So we want to completely factor numerator and denominator. Out of the numerator, greatest common factor is an 8x, so I pull it out. That leaves me with x squared plus 2x plus 1. I identify this as a perfect square. That's x plus 1 squared. For the denominator, we note here, this is just x plus 1 times x plus 3. Here, I can factor out an x plus 1 out of the numerator and denominator, leaving me with 8x, x plus 1, x plus 3, and I can't cancel any further. Note, we can't cancel any further, which means I can't split up this x plus 3 in the denominator, so we stop there. Here's an example using exponent rules. We have 3s cubed times t plus 1 squared over 9s t plus 1 to the 4th power. Note here we have 2 variables. We also have an expression raised to powers. So the idea is we're not going to expand that t plus 1 to powers out. That'll make things more complicated. We treat the t plus 1 as its own variable. Then we just apply the exponent rule. So for this problem, first step, 3 over 9 goes to 1 over 3. S cubed over s. Applying the exponent rule, that's s to the 3 minus 1, or s squared. For the t plus 1 terms, what are we going to do? Put this in the denominator of t plus 1 raised to the 4 minus 2. So that leaves me with s squared over 3 t plus 1 squared. Common error, don't let this 3 travel up into the numerator. Next example, we gave our special factoring rules a workout. I have 4x squared minus 1 over 4x squared plus 4x plus 1. In the numerator, we have 2x quantity squared minus 1 squared. So that's a difference of 2 squares. In the denominator, I have 2x squared on one end, 1 squared on the other end. In the middle, we have 2 times 2x times 1. That's a perfect square. So these factor as 2x plus 1, 2x minus 1, over 2x plus 1, 2x plus 1. We cancel, and we're left with 2x minus 1 over 2x plus 1. Now, note here, we really don't have a good way to check our work. So if you're in an exam or homework situation, the check on your work is that something actually cancels. We wouldn't ask you to simplify something if it didn't simplify. So we cancel something here. That looks like it could be correct. With that, we have a hint as to how to do our factorizations if we know how to do one of them. So for example, if I have 4x squared plus x over 4x squared plus 13x plus 3, note in the denominator, probably you'd want to use something like the AC method to pull that apart. But if we factor the numerator, 4x squared plus x is x times 4x plus 1, only candidate for something to cancel there is the 4x plus 1. So if that divides into this, the candidate for the other factor is going to have a 3 here and a 1 here, x plus 3. If I FOIL, then we see that that actually matches up with what we have here. So we cancel, and then we're left with x over x plus 3. Now, one item that needs special care, working with these rational expressions when there are minus signs around. So for instance, there are two things we want to pay attention to. If we have a rational number or a rational expression, if we have a minus sign out in front, I can either move it to the numerator or the denominator. But when I do that with a rational expression, I have to take care with what we have here. So you should always treat your numerator and denominator as being inside of parentheses. Once you have that, the way I distribute a minus sign, okay, we have to push this to each term. The effect is to change the sign on each term. So if I had minus parentheses 2x squared minus x minus 4, that's the same as minus 2x squared plus x plus 4. Common error here, when you don't use the parentheses, the minus sign goes to the first term, and then you're left with the last two items here unchanged. Okay, and then that's going to mess things up. For example, let's consider 5 minus x over x minus 5. Note, the numerator and denominator are just off by a minus sign here. So what's the work for that? There are two ways we can go. Using the previous board, okay, I can factor a minus sign out of the numerator. Okay, so note, we're just going to change the sign on each term, giving me an x minus 5. Now, we cancel the x minus 5s, leaving me with a minus 1 over 1, which gives a minus 1. Another way, we're off by a minus sign, so I want to change the numerator by a minus 1. If I do that, I have to divide by minus 1 at the same time. So if I multiply by something over something, we're just multiplying by 1. No change to our expression. Now, if I distribute that minus 1 to the numerator, we get our x minus 5. Minus 1 in the denominator, we're just going to leave alone until we get to the last step. So we get our x minus 5. They cancel. I have 1 over minus 1. Then that gives me our minus 1 again. So either way works. Now you can just take this as a rule. If I have a minus b over b minus a, okay, and a minus b is non-zero, that's always equal to minus 1. For another example, okay, we have x minus 7 over 49 minus x squared. We note expression in the denominator is a difference of two squares, 7 squared minus x squared. So that factors as 7 plus x, 7 minus x. Okay, note, we have to respect the order here to make that minus sign work out correctly. Note, these are off by a minus sign. So I could separate out the 1 over x plus 7 and then deal with this separately. So you can either use your rule to get a minus sign, or you can factor out the minus 1 from the denominator, whichever way you like. Wind up with a minus 1 over x plus 7. One more, just a little bit more complicated. I have 12 minus 4x over x squared plus 2x minus 15. Now, in the numerator, I can factor out a 4. That gives me a 3 minus x. Okay, so sometimes a better way to deal with this first step is to actually factor out the minus 4 to leave you with the x minus 3. But if we do it this way, okay, what do we note? If I want to use my rule, I have to factor the denominator. That's going to give me an x minus 3, x plus 5. We'll pair the 3 minus x with the x minus 3 off to the side. That goes to a minus 1, giving me a minus 4, x plus 5. We get cancellation, so that checks my work.